Okay. I think Mustafa has not been here, so let's get started. So the first talk will be Bobo. He will be talking about the curvature conditions on graph. Yeah, Bobo, please go ahead.
Thank you very much for the introduction, and thank you very much for the invitation for all the organizers. It's a wonderful meeting. So if something wrong in my talk, please tell me. So today I will talk about some curvature conditions on graphs. In fact, we already see some definitions in previous talks. So, by the way, I want to say that we have many friends in Chongqing University of Technology. They are geometers. It's great. So today my talk is based on two joint works with Yanhui Su and Florentin Muench. Su is from Fuzhou University, and Florentin Muench from Max Planck Institute in Mathematics, for mathematics in the sciences. So if you are interested, you can check these papers, which I will report some results in these papers. I will also mention other co-authors, Jürgen Jost and Shiping Liu. Yeah, Shiping is here also in the conference. So in fact, my talk is about curvatures. So as you know, there are so many curvatures on graphs. So in my talk, I will concentrate on Gaussian curvature for planar graphs. These are two-dimensional, and a high-dimensional curvature called the Ricci curvature. Okay, so let me start from the two-dimensional case, planar tiling. So it's a very old problem to tile the plane using variance tiles. So in our talk, we think of tiling whose tiles are regular polygons. So regular polygons are really those polygons has equal inner angles and equal side lengths. So you can see that these two tilings of the plane. On the left-hand side is the square tiling, and on the right-hand side is hexagon tiling. So let's try to generalize it. So maybe you use different tiles to get a planar tiling. For instance, in this picture, you can use different combination of regular polygons to get a tiling of the plane. So a very old problem is try to classify all these kinds of tilings. So in fact, there are infinite many, and up to now, it seems impossible. The classification can only be how one can only classify those tilings with symmetry. For instance, you fix several type of tiles, then you may classify this kind of tiling under symmetry. So in my talk, I think about all kinds of tiling. So maybe quite general, but it's not. So before the talk, I will introduce some terminology called the planar tessellation to rule out very strange tilings. So my tiling is somehow quite regular in the sense these three conditions. First one is somehow easy to understand. I assume that each tile is a disk. I don't want to have some like annulars to be a tile. And then we also assume that each edge is containing exactly two faces. So this is somehow reasonable. The third one is a very strong one. Any intersection of two incident faces, either a vertex or an edge. So we also assume that each vertex has a degree at least 3, and each face has at least 3 edges. So these are assumptions in my talk for planar tessellation. Usually I call it a planar graph. So, but you know that we have a lot of planar graph which are not tessellations. So this is an example 2 Violet condition 3. So recall that the intersection of two incident faces is either a vertex or an edge. So now you have two faces. The intersection of these two faces are two edges. So this is not it's not allowed in our setting. But you can imagine that if you further refine the tiling, you will get the, some triangulation or something. You can have a really tessellation. So once you have a planar graph, this is something topological. You don't have anything geometrically. So we want to have some metric structure so that we can study geometry of the planar graph. So we endorsed some metric, some canonic metric, which coming from the following sense. So you assume that each edge is of length 1 and fill in each face with a regular polygon. Then you group each face around common edges. In the following picture, you see that on the left-hand side is some topological object. Then after the this kind of in the canonic metric structure, each face is a regular polygon. So on the right-hand side, you have a regular triangle and a regular perfect square, right? So this is a picture to show the metric structure. So on the left-hand side is of course a planar graph, an infinite planar graph, but you see that each triangle is not a regular triangle. So after you endorse some metric, you get the graph on the right-hand side is a metric space. Each triangle is a regular triangle. So this is another example. So this is we are studying the object in the graph theory. You have 4 triangles. So outside, you have a outside triangle. So if you endorse the metric, you get a tetrahedron in the 3-dimensional Euclidean space. So each face is a regular triangle. So this is a metric structure SG. A more interesting example is following. So if you have a infinite planar graph, consists of a pentagon and infinite many hexagons. So this is on the left-hand side G. So then after you put some metric structure, you will have some metric space. So this metric space you can realize as a some convex polygon in 3-dimensional Euclidean space. You see on the right-hand side. So this is what I want to talk about the Gaussian curvature. So after you give the metric structure, there are some curvature. So as we know that a surface in three-dimensional Euclidean space, if the surface is smooth, you have the Gaussian curvature. So Gaussian curvature really have some geometric meaning of the convexity. For instance, if the Gaussian curvature is positive, is the left picture is the point has a positive Gaussian curvature. So somehow it's convex here. So in the middle, this picture has negative Gaussian curvature. So this means somehow you have two different direction of bending. So this is kind of a negative picture, the negative curvature. Then zero curvature means there is one direction, somehow has no bend, it's not bending, right? This is okay. So Gaussian curvature is very important in the geometry. So in my talk, I will discuss this discrete Gaussian curvature. So in the continuous case, Gaussian curvature really means convexity. So if you have a convex surface, which is a boundary of a convex body in three-dimensional Euclidean space, then the Gaussian curvature is non-negative. You see the following picture. So this is a definition of discrete Gaussian curvature in the piecewise flat space. So at the vertex x, you have three polygons. Then you can calculate the total angle at the vertex x. Here I denote it as sigma x. It's the total angle. Then you use 2 pi minus this total angle to define the discrete Gaussian curvature. So easy proposition is following. So in our previous discussion, planar tilings are of zero curvature everywhere, right? So each vertex has total angle 2 pi, so zero curvature is flat. So this definition is somehow natural. We cannot find the exact first one to define this curvature, but you will see that there are a lot of references which define this Gaussian curvature again and again. So in the planar graph setting, as I said, you can define kind of so-called combinatorial curvature in the graph theory. So it's defined in the following formula. So if you calculate the discrete Gaussian curvature, you divide it by 2 pi, you in fact get the combinatorial curvature. So in a graph theory, people study combinatorial curvature, but in fact it's just some multiple of the discrete Gaussian curvature. So let's talk about some examples. Planar graphs with positive curvature. So there are a lot of examples in three-dimensional Euclidean space. Some convex polyhedral whose faces are regular faces or regular polygons. So this is the classification of polygons with regular faces in R3. So you can find a lot of examples. So in this case, if you think about the Gaussian curvature, it has a positive Gaussian curvature at each vertex. So these are examples of planar graphs with positive curvature. So these are two interesting family of graphs with positive Gaussian curvature. The first line called the prism, and the second line called the anti-prism. You can imagine that there are infinitely many such examples. But we will see that these are very special two classes. Other has you have only find many examples. So let me denote some notion called it graphs, a planar graph with non-negative Gaussian curvature or combinatorial curvature. This is PC non-negative. So as we observed before, so if a planar graph has non-negative combinatorial curvature everywhere, in fact means at each vertex you have non-negative Gaussian curvature. So the SG is a metric space associated to this graph. It is a convex surface in the weak sense. So there are some well-studied object called the Alexander space. I will not mention this. This is just means convex surface in the generalized sense. Okay, this is another interesting example. So in the chemistry, people find some very interesting structure called C60. These are they call it furan. So furans are, you can define it as in the abstract way. So these are planar graphs, finite planar graphs. Each vertex of degree 3, and each face is either a pentagon or a hexagon. So this is the definition for the furan. So there are a lot of furans. So these are pictures for furans. So really you see that furans can realize as a boundary of a convex body in three-dimensional Euclidean space. Somehow you can see. And you can have a lot of, you can have infinite many furans. So these are very interesting class of graphs with non-negative curvature, because at each vertex, incidence to 3 hexagons, the curvature is 0. On the other hand, there are a lot of studies about negative curvature planar graphs. So you can see the reference if you are interested. Also, in some paper by Matthias Keller and Professor Pyrenhoff. Yeah, there are a lot of studies of negative. So in the negative curvature case, these are discrete analog of hyperbolic space. So you can study the isoperimetric inequalities in that case. So in my talk, I will concentrate on graph with non-negative curvature. In this study, a very interesting theorem proved by Bobo Hua, which was conjectured by Gucci before. Any planar graph with positive curvature is a finite graph. So they can also estimate the number of vertices in for such kind of planar graph. The number of vertices is at most this 3,444. So of course you need to exclude presence and anti-presence. There are infinite many, right? Okay, so if you move to graphs with non-negative curvature, you have so many examples, and there are infinite graphs. So in the early work with Professor Yost and Shiping Liu, we studied this kind of graphs with non-negative combinatorial curvature. Then you can prove a lot of results which are motivated from continuous setting. So a convex surface has a quadratic volume growth. So somehow you can prove that a graph with non-negative curvature has quadratic volume growth. And you can prove that there are many analytic results like volume growth property, volume doubling, and Poynting inequality. So somehow you can study discrete harmonic functions on such infinite graphs, and you will prove kind of properties of harmonic functions of polynomial growth. I will not, if you are interested, you can check this paper. So my question here today is, so we want to construct planar graphs with non-negative curvature. Of course, we know that planar tilings are examples, but we want to see other, maybe other examples. Of course, a graph with non-negative curvature has a lot of obstructions. So we want to find some obstructions for constructing graphs. So first result is about total curvature. So total curvature is if you sum over all vertices, the combinatorial curvature. So we denote as total curvature. So note that this might be an infinite graph. So you need to prove this quantity is finite. And this is the final result joined with Yanhui Su. We can prove that if an infinite graph with non-negative combinatorial curvature, then its total curvature is an integer multiple of 1/12. So it's very restrictive for the total curvature. The total curvature takes value in a discrete set. This is first theorem. Another result you can show. You can study the set of vertices with positive curvature. So here I denote as TG is the set of vertices with positive curvature. So a previous result by Beifang Chen and his courses proves shows that the number of vertices with positive curvature is finite. In a joint work with Su, we can prove that the number of vertices of positive curvature is at most 132. If you exclude some trivial examples like prisms. So this is a prism-like graph we want to exclude. So this graph is constructed in the following way. If you have a face, a very large face, sigma, then you can construct something like a half cylinder. So you can use squares, triangles, and go this direction infinitely many times. You get an infinite graph. Of course, this graph has non-negative curvature, but you can have arbitrary degree of this face. So somehow you cannot control number of positive curvature because each vertex on the boundary of this sigma will have positive curvature. So to exclude such kind of trivial examples, you can prove that the number of positive curvatures vertices are at most 132. This is an example with 132 positive curvature vertices. So if you are interested, you can check that. So I want to talk about the total curvature results. We prove that the set is discrete. So somehow I want to give a proof here. So the first one is well known. If you see that the Euler's formula is well known for convex polygon. And in the Riemann geometry, there's a so-called Gauss-Bonnet theorem, which means the total curvature is related to the Euler characteristic of the surface, closed surface, without boundary. So the discrete Gauss-Bonnet, you can use discrete Gaussian curvature, and the proof of the discrete version is somehow trivial, or in some sense, is equivalent to the Euler's formula for convex polygons in three-dimensional space. Okay. So this Gauss-Bonnet theorem has a generalization by Huber or conversion. So if a non-compact surface, if under some condition of the integrability of the negative part of the Gaussian curvature, you can prove that total curvature is at most 2 pi times the characteristic of the surface. Okay, this is really a very classic theorem in Riemann geometry. People prove this in a discrete case. So you can, I stated it in the following way: if infinite graph with non-negative combinatorial curvature, then the total curvature is at most 1. 1 because 1 is the Euler characteristic of the plane. So this is really a discrete version of Huber. Sorry. So I want to say that maybe these two theorems in fact are exactly the same. So another thing is total curvature has some geometric meaning. I want to mention that a convex surface has some is associated with a cone at infinity. So the total curvature is related to the cone angle of the convex, this kind of cone at infinity. So in the continuous case, non-compact convex surface, the total curvature for such surface takes value from 0 to 2 pi. So it's continuous. This is an interval. But in the discrete case, you somehow, as our result shows, it's discrete. So this is an example for non-negative combinatorial graphs with combinatorial curvature. So you have on the left-hand side and the right-hand side, then you group the edge A and the edge B. Somehow you have a example. So excuse me. So this is a second example. You can construct many examples with non-negative combinatorial curvature. So now I want to talk about the proof. So the proof uses Gauss-Bonnet theorem for some domain in a surface. So and also a result by Guantao Chen and Beifang Chen. They show that number of number of vertices with positive curvature is finite. So these are two ingredients for the proof. So let me quickly show the idea of proof. So this is a graph with non-negative curvatures. There are finite many vertices of positive curvature. So you find a very large domain, omega, to enclose or to surround the positive curved vertices. Then you see that the summation of curvatures of for vertices with positive curvature is exactly total curvature. So come return to the previous formula. So this is the Gauss-Bonnet theorem. This is somehow Gaussian curvature in the domain omega. So in our case, if you choose omega sufficiently large, this will be a total curvature for the surface or the plane graph. Then the second part is the integral of geodesic curvature in the continuous setting. Then in the discrete case is a summation of the outer angle at each vertex on the boundary of omega. So then the right side is the characteristic of the domain omega. So if you want to prove our previous result, somehow this quantity is what we want to show, and this is somehow known. You only need to control the summation of outer angles around the boundary of omega. You just prove that it is a discrete set in some sense, right? Then you can estimate, you can analyze this vertices on the boundary of omega. It is of zero curvature. Then the pattern is means, for instance, 3, 7, 42. This means this vertex is incident to a triangle 7-gon and 42-gon. So in this case, you have zero curvature. These are all possibility of zero curvatures. So it's quite restrictive. Then you see that it's a discrete set, right? Then further, you carefully analyze the examples. You can exclude the cases. You can prove that the total outer angle will be an integer multiple of pi/6. Then you can prove that the final result is integer multiple of 1/12. Okay, so that's a proof. Okay, let me talk about the rich curvature. So a celebrated result of Shinton Yao is for a Riemann manifold with non-negative rich curvature, any positive harmonic function is constant. The proof of Yao, you can use so-called Chen-Yao gradient estimate for a positive harmonic function on a ball of radius r. The gradient of the function at the center of the ball can be estimated above by this UP divided by r. This is a very classical gradient estimate. Then you let the radius of the ball tends to infinity, you get the gradient is 0, then the function is constant. Okay, this is really amazing result for in the geometry. Now I talk about the setting of graphs. Maybe I quickly go through that. So we are considering graphs. On each edge there is a weight mu. On each vertex we have a weight mx. We call it a weighted graph. Use the weights, you can define the Laplacian, discrete Laplacian. In our setting, we choose the weights at the vertex as the total, the summation of the weights on edges. So in this sense, we call it normalized Laplacian. So today, maybe we talk about normalized Laplacian. Then this is related to a simple random walk on the graph. Okay, so if a function has a Laplacian u equals 0, we call it a harmonic function. So for the harmonicity really means the mean value equality for the ball of radius 1. So the vertex A is on the graph, the function value UA equal to the mean value of its neighbors. So this is means harmonicity. So to prove some results, we need a curvature. So as Professor Peinhof already introduced the Bakry-Emery curvature, I will quickly skip that. So use the Bobo type inequality. You can define so-called Bakry-Emery curvature or curvature dimension condition on graphs. So this here, rich X means somehow the base constant K holds for any F. So this is called Bakry-Emery curvature. Then use their software. You can find some examples, like you can see that this is positive curvature, which somehow close to a complete graph. This is a dumbbell. Dumbbell has negative curvature in the neck, and you have a tree. If the tree goes out, you have negative curvature. So quite close to the geometric meaning of curvature. So I want to say that if the graph has non-negative curvature, then any boundary harmonic function is constant. This proof somehow use the analytic property of heat equation. So we cannot prove it at the moment use elliptic estimate. We can only prove it use a parabolic estimate. So for the harmonic function f, which is bounded, you use the heat equation evolved with inertial data f. Then use the curvature condition CD0 infinity. You can estimate the gradient of the solution at time t. Then let t goes to infinity, you prove the result. I want to mention that there are other curvature notion called the Ollivier curvature. A similar result about the boundary harmonic function is constant called the Liouville theorem for boundary harmonic function was proved by Muench and Rose. Also, you find in a different proof in Muench's paper. Okay, so Ollivier curvature, I don't have much time, so I skip the definition, which use the optimum transport plane, and these are examples for computation. This is dumbbell. Dumbbell has negative Ollivier curvature on the edge in the neck, and the tree has negative curvature inside. So for the last result, I want to mention some estimate some result in geometry. So Chi-Gourmaud proves that a manifold has non-negative ridge curvature, has very strong restriction for the structure. If you have a line means somehow some infinite geodesic both sides, then the structure of the manifold really splits as Euclidean product, not Euclidean, Cartesian product of low dimension manifold n times r. Using this result, a well-known corollary is the number of ends of the manifold is at the most 2. So an end of a manifold means you for a compact subset K in a manifold K, in a manifold M, if you delete the compact subset, then you consider the complementary of this K. There are infinite connected components. Each infinite component is called an N with respect to this K. So this is cylinder has 2 ends. This graph has three ends. So you can see if you delete this K, you have 3 infinite component, non-compact connected components. Okay, we can prove something quite similar to the corollary. So if you have a non-negative Ollivier curvature, then number of ends is at most 2. So if the number of ends exactly is 2, then somehow the graph is very special. It's like a line. So in the following picture, this graph has non-negative Ollivier curvature. In the largest scale, it will quite close to a line. So this is a second statement. So but in the next picture, if you carefully choose the weights on edges and the vertices, you can produce an example with non-negative Ollivier curvature. So on the second graph, this looks quite strange, but somehow the weights tends to infinity. So you need to add some condition like bounded geometry to exclude such kind of strange examples. Okay, I quickly talk about the proof. So in the classical proof of Cheek-Gromov splitting theory, use the Boltzmann function. So this is somehow always crucial to the problem. Boltzmann functions are harmonic functions. If there is a line, then but on a graph you have the nature distant function. You can define the Boltzmann function, but which are not good enough, which may not be harmonic or subharmonic in any sense. But somehow in our proof we find some way to replace the role of Boltzmann function. So we construct some linear growth harmonic function, which has some Lipschitz using kind of Lipschitz extension. So if you are interested, you can you can take the paper. I don't have much time. First, how to prove there are only three, at most two ends. So first one, there is such kind of Lipschitz harmonic function. The level sets are finite. Then you can prove the graph is recurrent. Recurrent means parabolic in the geometry. So this already means that it's quite restrictive. So if you have three ends, on each end you can construct such kind of Lipschitz harmonic function. Then you consider summation of all these harmonic functions. You will see that it's bounded from below and harmonic. So use recurrence, H is constant, you find the contradiction. So it's impossible to have more than three ends. Final result is all harmonic function on such graphs is of finite dimensional. And if the harmonic function is sub-exponential growth, then it's only two possibilities. One is constant, another is linear growth. The final one is Chen-Yao gradient estimate holds for such graph. So you can prove Chen-Yao gradient in this setting. Okay, I will finish the talk by posing some conjectures. So for graphs with non-negative curvature, in any sense, if you like, then you assume that the graph has bounded geometry. We conjecture that harmonic function has Liouville theorem, and Chen-Yao gradient estimate should be true in some sense. And finally, Cheek-Gromov splitting theorem will be true in some modified sense. So the last conjecture is not a conjecture because we don't find the proper formulation for the Cheek-Gromov splitting. For instance, this graph, which is a Cayley graph of the abelian group, which has non-negative curvature in many cases, but you cannot find the Cartesian product structure for this graph. Okay, so to have a proper formulation for Cheek-Gromov splitting theorem is still open problem in even for the statement is open for us. So thank you very much for the for your attention. Thank you.
Thank you so much, Bobo. Is there any question for the speaker? Yes, Junji.
Yeah, hi. I'm thinking along about applying this combinatorial curvature for some of these applications in biology and stuff like that. I'm wondering, like, has people because the combinatorial curvature is quite different from the later part of the talk, like the Ollivier rich curvature and stuff. So the combinatorial curvature is defined vertices and things like that. So is it possible to define it on let's say the edges or the triangles if we do some triangulation and stuff like that?
Yes, so combinatorial curvature is you assume each face is regular, but somehow you can define the discrete Gaussian curvature in this way. So if you have a triangulation, then if you can calculate the angles at the vertex, you can define as a discrete Gaussian curvature. Then there are many studies called it rich flow use Gaussian curvature, like the well-known result by Ben Chao and Luo Feng. They can study the rich flow to deform the edge length in some sense, but somehow they use the circle packing structure.
I see. So
Yeah.
so you still have to go through some of these triangulation.
Yes.
I see.
Yeah. The triangulation you because you have the edge length, then you can somehow, if each face is somehow flat, Euclidean triangle, then you can calculate the angle. Then you can define the curvature at the vertex. Then somehow you can deform the structure by curvature using idea of rich flowing something.
I see. I think that explains why the Ollivier rich curvature is more popular than for the applications.
In application, because somehow Gaussian curvature restrict to two-dimensional like planar graphs, but Ollivier curvature is defined for any graphs. So you can maybe in the application sense, it's more popular for Ollivier curvature. So, but somehow in the geometry, in particular for the surface study, like hyperbolic surface and
Yes.
it's very popular. It's very good definition. By the way, so if you define three-dimensional triangulation of a three-dimensional manifold, somehow you can use called it dihedral angles to define the curvature. Then these are very useful also in three-dimensional cases.
Yes. Okay, thank you.
You're welcome. Yeah.
Thank you so much. We still have 1 minute, time for 1 minute question. Are there any more questions for Bobo? Yes, Kellen, please go ahead.
Yeah, hi, Bobo. I'm wondering, is there any way that we can judge if a very complicated graph is a planar graph?
So if a graph is planar, there are a lot of criteria, if I understand you.
So you need to make sure the fill in each you have the definition, right? But I'm saying that computationally, if I have a very complicated graph, right? Is there any way that I can automatically check that if this one is a planar graph?
I believe it should be in a graph theory. People so a graph is planar if there is no something like a K4 subgraph or something like that. There should be some effective way in the graph theory.
I see. It's interesting. And then you mentioned about this discrete Gaussian curvature, and then later you have another one like phi x equals 1 minus degree over 2. That definition, I guess I missed that one. Yes, this one. So what is the difference? This one is on the planar graph. So what can you say a little bit more about this combinatorial curvature? How it relates to the previous one?
Yes. So if you have a graph, then if you fill in each face with a regular polygon, then you can calculate the discrete Gaussian curvature, use total angle, sigma x.
Yes.
Then afterwards, you will see this formula. Exactly 2 pi times this quantity. The Gaussian, yeah.
I see.
Because
I see.
because each face is a regular polygon, the angle is very, very easy to give a formula. Then you take the summation, you get this.
I see. I see. Got it. Yeah. Thank you.
You're welcome.